The current one, yeah. Yeah, but okay, it will have the same problems basically as the Intel Pentium 4 processor. We have two instructions issued per cycle. It's not very interesting. Split cache, and it's also, this is basically the part which supports virtualization. Yeah, that's not supported by the SPEs or something. It's supported by the PPE, of course. Yeah, to say overall, it's a simplified power architecture to run at these high frequencies. The synergistic processing element is the thing which is interesting at the processor, at the whole cell processor, because we have 8 of it. It's a very small processing element, but it's just the amount which counts. We also see that it's occupying most of the, altogether, most of the floor plan. And yeah, it's connected with the EIB. And each of it is a fully blown vector CPU. So it has own RAM, SRAM. It's not a cache, so there's a difference between RAM and cache, you know. And this instruction set architecture of this CPU is not VMX compatible. So they just invented basically a new instruction set architecture, which is really completely new. So you have to relearn everything. That's not very nice, but yeah, it's very interesting. It has a fixed length. That's also a strict RISC approach of this architecture. And yeah, 21 million transistors, that's not being very interesting. But we see that's the storage, the local storage, and that's the calculation entity. And we see quite a lot of storage, and the register file is also quite huge. And we see why. Oh, not on this slide. It's, as I said, as I told you, it's a very, very, very simple processor. So it has no branch prediction or scheduling software. That's all which was achieved in the last years in processor design was branch prediction, scheduling, and out-of-order execution. And they throw it out because they want to get very, very high clock frequencies, and they want to move the complexity into software. They just going a totally different way to move the complexity up and to let the compiler or actually the programmer decide how fast the code will run on the processor. And we have two independent, very short, and simple pipelines. I don't know about the real pipeline depth, but maybe you can help me. No? It's maybe not published yet, I don't know. Yes, a very short one. And we can issue inside these two independent pipelines, 2 instructions in parallel. That's also very interesting because it supports overlapping of memory fetches with calculations. And that's a very cool feature. Basically every processor has it, but it's explicitly mentioned here. And we can do one memory and one SIMD computation. Basically every computation inside the PPE is an SIMD computation. So you're operating all the time on vectors. So it's a vector CPU. It's strictly in order. So yeah, they can't pass each other the instructions. And they all work with a 128-bit compound data. So compound data means that it can be a vector of 4 32-bit integers or 4 32-bit single precision floating point or 2 64-bit double precision floating point or something else. So like the normal data types we all know. We can process 4 single precision floating point operations per cycle. So it's pipelined, of course. We have a latency of the pipeline depth. And they are not fully IEEE compliant. So that's more or less for the scientific community, because some scientific programs rely on these special IEEE features like not a number or special rounding features. But I think it's not very important for the task of the for the task of the cell processor to just process multimedia data, because yeah, multimedia data is not very demanding in number accuracy or something. It doesn't matter if the pixels is there's a little bit different color or something. You just don't see it. And we have 4 single precision floating points per cycle. We assume 4 gigahertz. Then we have 16 gigaflop. And then we have this magic IBM fused multiply add instruction, which is basically doing multiply and add in parallel, so in one cycle. And we achieve 32 gigaflops. So this fused multiply add instruction is something, yeah, I think it was designed for the top 500 list, just to to push the systems up. Sorry, IBM, but we've made several investigations that it's really very, very, very useful for scientific programs, and that's it. So I don't know how useful it will be for designing multimedia or streaming applications, but for scientific programs, it's a very useful command. Then we have unfortunately, a very slow double precision arithmetic, which is nearly fully IEEE compliant, and it's quite slow. And it's also not fully pipelined, and there's also another restriction. You can read everything in the programmer's manual, which is quite thick, I think 200 pages or no, 600 pages. And yeah, for example, after issuing a double precision command or instruction to the processor, the next 6 clock cycles, no instruction can be issued. So it's just blocked for 6 clock cycles. And so they can't give you a direct number for the gigaflops, because it depends how other instructions are going to the pipeline, and because of this blocking. Yes, and we can process, of course, 4 integers per cycle. That's just the normal vector processing approach. And that's a block diagram of the SPU. We have the local storage. It's 265 kilobyte. That's all RAM we have for our programs. So we have to write very small programs. We can fetch more. We can access the whole system memory through DMA. But basically, we have to stick with this 256 kilobyte. And the instructions are also inside the 256 kilobyte. We have this two-way issue, even and odd pipeline. Both pipelines operating on these 128 registers, and yeah, doing all this stuff. So interesting is the distinction between calculating pipeline and memory fetching pipeline. So they're operating in parallel, of course, would be no pipeline. And we can double buffer very, very efficiently with these processors. We can fetch an instruction and calculate the next one. No, we can calculate an instruction and fetch the next data item, for example, then swap buffers, calculate the data item from the previous fetch, and fetch the next one. So that's a very interesting principle in scientific computing, just to overlap computation with the data fetching, and you achieve nearly 100% of the theoretical peak, because you don't stall at memory fetches. Yeah, the memory can be accessed in 120-bit, 28-bit lines. Yeah, that's not very. That's optimized for bulk transfers. And interesting is also registers are layered. There's no distinction between, for example, floating point registers or general purpose registers. Everything can fit into a register, as it is a vector data type. So floating point data and integer data are residing in these same registers, basically. We have no virtual memory or no coherency on the local storage. We have no processing in main memory. So we have to fetch the data item into our local storage. And even more, we are also not allowed to, or we cannot process on the local storage. So we have to fetch the data item into the registers, because it's a RISC design. It's a strict load store architecture, as we all know. Then, yeah, the DMA, I already told this. The MFC, basically the memory flow controller, connects to the EIB and does some additional tasks, like the MMU in our traditional x86 architecture does. So it holds a small page table, and well, this is going to be a little bit more complicated because it has no access to the global page table. So basically the PPE has to tell the SPU for the actual running process, which pages it's going to access. But that's a programming detail, it doesn't matter here. And it does synchronization, because we have a parallel system. basically we have a parallel system on a chip, and we have to synchronize between these tasks, units. Okay, how are we going to program it? Typically, we are going to spawn user-level threads. So we just run a program. It starts at the PPE, and then it spawns off a thread on the SPE. So yeah, the thread is not like a normal thread like we know, because it has a different binary. They have a different instruction set, so we need different binaries. So we just tell the PPE to load a binary into the local storage of some SPE, and then the SPE to execute it. That's how it works. And we have that's going to be very complicated. I tried to program it, and that's awful at the beginning. But IBM is very kind and gives us an IDL tool. It's called Interface Description Language, and it supports RPC programming. So basically, we can define a small function which is going to be on the SPU, and which we are going to offload. And it's, we just use this IDL tool, and it does everything for us. It defines the interface, it cares for the loading of the instructions to instructions and data to the PPU. No, not PPU, of course not. SPE, sorry. And it triggers the SPE to execute the program and gets all the data back to us. That's very, very nice, but also a little bit limited. I'll show you when I have time. We can do, of course, assembler programming and also C and C++ programming. We are provided with several C and C++ intrinsic functions. That's very nice. So we don't have to use the assembler, inline assembler to use the special features of the SPU. We just have functions like SPU add, SPU mul, SPU diff, which acts on vectors, vector data types. So we have new data types. We just pack your data in, and I'll show you a program later on. And we have no access to the system control table, I told you. And the local storage is unprotected and untranslated, so we can't implement an operating system inside a SPE, for example. So we can, but it's going to be hard. It's a strict load store architecture. Yeah, okay, I told it. So, just a small comparison. This is the Opteron floor plan. It's about 114 square millimeters. It runs at 3 gigahertz, for example, and can issue can finish two floating point operations per cycle. Okay, I'm talking of single precision. And the SPE is down here, and it's running at 4 gigahertz and can finish 4 single point floating point per cycle. So we see it's really fast. And the Opteron is not a bad processor. But if you would compare the double precision, the Opteron would be much better. But I just wanted to show something that's really amazing. And we have 8 of them. Yeah, you have to remember, we have 8 SPEs. And all connected with the element interconnect bus. That's the thing in the middle, which is connected to all entities of the cell processor. It has 4 128-bit wide concentric rings. So the data is just passing around in a ring. And we can transfer 96 bytes per cycle. So you should just try to calculate which data rate we have. So basically 4 gigahertz, and it's nearly 400 gigabytes per second we can transfer on this bus. And it's very interesting that it's a buffered point-to-point ring. So everything is independent. It's not really a bus, it's more a ring than a bus. So if you know SCI, you just send an item to the next entity, and it stores it and sends it to the next if it's not for the entity itself. And so we have, for example, also a guaranteed bandwidth, because I can just take my slot when I want it, because I'm going to forward the data for others, and it's just up to me if I want to take my slot, I take it. And the SPE, better to say the MFC, so the memory flow controller, has the duty to route the traffic. So it's also very, very scalable. We can add more SPEs as we want. Just the latency to reach another SPE increases. but we will see that there are very, very efficient ways to overlap, and so we can see that these latencies